So we had just seen our first example of doing an indefinite integral with the substitution method. We kind of just felt our way through that first example, but now here's the actual theorem for the substitution method that says, okay, we can actually do this. So we're going to start by letting our substitution variable u equal g of x. And that g of x is going to be some part of our original integrand. So letting u equal g of x, if we want to take the indefinite integral of f of g of x times g prime of x dx, the substitution method says that we can convert this over to a function of u instead. So we're going to take the indefinite integral of f of u du. So you can see that g of x getting replaced by u, and the derivative of that g prime of x dx is getting replaced by du. So this is actually what we did in the example here by finding a u function that has its derivative sitting in our integrand. And then we found du to kind of replace the rest of the integrand there. So that is our theorem for the substitution method. And as you can imagine, making an appropriate choice for u, letting u equal g of x, that's going to be key to solving these type of problems. So here's some ideas for choosing u, because u can be anything. Yay, good life lessons there. You can be anything. But in a substitution method problem, here's some ideas for choosing u. The first one is basically what we did in our first example. We're going to look for the derivative of something, look for du sitting in the integrands. Okay, because if you see a little function and its derivative sitting in your integrand, that means you're identifying this little piece right here and its derivative is sitting in the integrand. That's going to be a good choice for your u substitution there. Another idea, if you don't spot like the derivative of something sitting in your problem, the idea of these, remember, is to make an easier indefinite integral problem. So sometimes it's a good idea to just choose whatever looks complicated and turn that into u. Okay, so choose the complicated bit. To be your substitution spot. All right, because then hopefully that will simplify down your integrand and allow you to actually find the antiderivative if you kind of take out that complicated bit. And then the third idea here is really just to try something. Look for any piece of your integrand that you could possibly turn into a substitution and just try it. If it doesn't work out, you'll see that it's not working out, and then you can go back and try something else. And these do get easier with practice. So if they are a little tough at first, don't worry. I mean, that's normal. You're not alone. Just try something until you start seeing some common patterns start to come up, because there's going to be setups that tend to arise over and over again. And so in the meantime, until that starts happening for you, just try something and see if it works. Okay, so let's do a first example here. Okay, we're going to take the indefinite integral of 1 over t minus 6 to the 4th power dt. Okay, so our first step here is going to be to choose what we want u to be. And let's see, it looks like, well, maybe not a There's not a super clear du sitting in the integrand here. If you do spot one, that's cool. Go for it. So how about we choose the complicated looking bit to be our u? Okay. And what's making this complicated here is really the fact that we've got t minus 6 to the fourth down in our denominator, rather than just like t to the fourth. Because, you know, if this was 1 over t to the fourth dt, this would not be so much of a problem. You'd just turn that into a negative exponent and you'd find your antiderivative. So that would be like totally cool. So let's make that part that's complicating this integrand into our u choice. So let's let u equal that t minus 6 that's complicating things. And now we want to be able to convert the entire integral into terms of u. So t minus 6 there, that's going to be our u. Okay. And so what we still have left to convert is the dt right here. We don't want that to be in terms of t. That's not good. So let's work with some differentials here. Take the derivative of u with respect to t, du dt. And the derivative of t minus 6 is just going to be 1. 1 minus 0, yeah, but just 1. So if we work with the differential du, that's going to be 1 dt, or you could just say du equals dt. Okay, and so we can see that this dt right here is actually going to get replaced with du, because du equals dt. And so we can take this indefinite integral and make a new indefinite integral. All right, we've still got this 1 up in the numerator. That's okay. That didn't have a t in it, so we didn't really need to focus on converting it. 1 over, but now we have u to the fourth power down in the denominator. And instead of dt, we have du. Okay, so this is exactly what we were talking about there. We have the integral of 1 over u to the fourth du. And so now we just focus on this. And how we would solve this is by making that into a negative exponent, u to the negative fourth du, and finding the antiderivative, right? So the antiderivative of that would be u to the negative third, add 1 to that power, remember, right? And then we'd need a negative 1 over 3 out front. And don't forget your plus c, because these are all indefinite. So keep that plus c there. So we've gotten the antiderivative of our converted indefinite integral. So this is in terms of u. But now we need to go back through our substitution and get this back in terms of t. So we are going to put back in the fact that u equals t minus 6. And we'd have negative 1/3 t minus 6 to the negative third power plus c. Okay, and that is actually one form of a viable answer. You could also say this is negative 1 over 3t minus 6 to the third plus c. That would also work. Either one of these, they're equivalent. But the idea here is that now we've taken that antiderivative, taken this indefinite integral, and gotten it back in terms of the original variable t. You don't want to stop when you've gotten it in terms of u, even though that can be tempting. You're like, yay, I got the antiderivative, but it needs to be put back in terms of the original variable to truly be the solution. Okay, so that's how this is going to work. And in the next video, we'll do a couple more examples.